So, coming back to structural VAR chapter, estimation techniques. The parameters of SVAR, theta is S beta 1 up until beta p, in which, as we know, for short-term restriction we have root d divided by b naught. S is equal to root d divided by b naught, which is the casual equation we have used earlier significantly. But S becomes phi 1 multiplied to f in terms of long-run restrictions. The parameters can be estimated using iterative algorithm by maximum likelihood conditioning on the first p observations. So the log likelihood function in this case is simply 1 by t minus p, because we are talking about this iteration running up until the first p observations, or in other words we can say the first row observations. So the log likelihood function equals 1 by t minus rho summation of log likelihood function, which will start from row plus 1 up until t. So this is something we need to remember. So we don't have to mention it row. I made a mistake here. If you have S, just like before, if you go back when we discussed our VAR structure with S, it's the same equation, 1 by t minus s, and t equals s plus 1, where s is equal to maximum p and q, maximum of p and q. So we can condition, in this case we can condition make the conditions or condition upon the first p observations, a selected number of observations, so that can be t minus p. But remember, our iteration will begin from p plus 1 in all cases, so that whether we are talking about s plus 1 or p plus 1, because this equation has been repeated before. And there are two strategies that depends on if log likelihood function is expressed in structural or reduced form. So in terms of structural form, we have half minus n by 2 log twice pi mean log determinant of d, the diagonal elements of the variance covariance matrix, 1 by 2 t minus p t p plus 1, and this is the decomposed equation, decomposed element, or the decomposition element, u transpose u divided by d, where d is the diagonal element of our equation of a residual, right? Because u is id with 0 mean and d standard deviation. So d variance, these are diagonal elements, and this is the regular equation beta I by t minus I plus ut, as you know. In terms of reduced form representation, we use omega, which is u transpose divided by d by default. So the reduced form is simply minus half log twice pi minus half log determinant of v, just like before, or omega 1 by 2 t minus p u transpose u and omega v. V is equal to ss transpose, s is equal to root over d divided by b naught, and so d divided by b naught square is your v. Because both are full information, maximum likelihood, both give some results. Generally SVARs are estimated with reduced form, so we generally use the reduced form equation, and v, instead of v we write ss transpose, because historically VAR is estimated in the first stage. The information matrix is block diagonal. Estimation of the mean and the variance parameters can be performed separately. There are two stages of estimation. First, we are estimating the mean parameters. Maximum likelihood estimation of the VAR are obtained by maximizing log likelihood function with respect to the autoregressive parameters phi 1 up until phi p, with v concentrated out of the log likelihood function, omega concentrated out from the log likelihood function. This means each equation of VAR is estimated individually by OLS to yield autoregressive parameters up until p or rho, whatever you say. The var residuals are given by obviously taking v on the left hand side, omega on the left hand side. You have yt minus I is equal to 1 to rho phi I yt minus I, right, from the reduced form equation, which are used to compute the n by n covariance matrix, which is 1 by t minus p, summation of t is equal to p plus 1 to t vv transpose, right? So 1 t plus 1 to t vv transpose. So this is simply in the place of log likelihood function, right? Very simple. So we are using vt, the residual, to compute the n by n covariance matrix, which is a squared matrix, right? So that was mean parameter estimation. Now let's talk about variance estimation. In terms of in case of variance parameters, the maximum likelihood estimation estimates of beta naught and d in case of short run parameters, and also long run in case of f. So beta naught and d are in case of short term parameters. These are the parameters of MLE, and beta naught and f in case of long run estimation. This is the parameter f are obtained. We obtained all by maximizing the reduced form equation, which is half log to s pi half log omega v 1 by t minus p vv transpose divided by omega. Now where v is equal to s transpose, and for short run s is root d by beta naught, for long run is phi 1 f. So this is the maximization problem is exactly as solving a non-linear system of equations with v equals s transpose. V determined from first stage estimation. So we have already in the first stage estimation determined the variance covariance matrix. This expression defines the first order conditions of maximum likelihood estimations with respect to those parameters. From S, which is root over d by beta naught, in which case estimates of beta naught and d are obtained. So estimates of beta naught and d are obtained from S, estimated S, and hence estimated v indeed. So because S is equal to root d by beta naught, okay, so take it on the left hand side. If you know beta naught with s and you know d, if you don't know beta naught with s and root over d, you can find beta naught. If you don't know d with s and beta naught, you can find d. So in maximum likelihood estimation, the basing on our estimated s and estimated omega from the first stage estimation, beta naught and d are derived. Once beta naught is obtained, the beta i's are then obtained from beta I equals beta naught phi I. Very simple, where phi i's are obtained from var in very first stage. Obviously autoregressive parameters have also been estimated in the very first stage. So the first stage gives us estimates of omega, estimates of the structural residual, estimates of s from there. So because omega equals s transpose, so estimates of s is also derived. Taking those information that we have derived from earlier, we can find our structural parameter beta naught and a diagonal element d of the variance covariance matrix, and also beta I. When we find structural parameter beta naught, we can also find beta I. Very simply, another structural parameter from where autoregressive parameters have already been determined in the beginning. So an example, estimation of SVAR with short run restrictions. Consider a dynamic system of interest rate. So we're talking about an vector of interest rates, right? When R1t is an instantaneous yield, R2t is 1 monthly yield, R3t is 3-month yield, and the structural model is given by beta naught yt. or 40 might be a 4-month yield. Okay, so this is the reduced form model with unknown parameters. Now beta naught, when we solve for this equation, beta naught is first, in the first equation we have R1, which is 1 0 0 minus beta 2 1 1 0. Okay, so we are doing a lower triangular matrix, minus beta 3 1, so 0 and 1. Okay, so we are not talking about 4 interest rate, we're talking about 3 interest rates here. So R1, R2 and R3. So for R1 we have 1 0 0. For R2, obviously R2 will be affected from the will be affected by the lags of its earlier variable. So R2 will be affected by earlier variable indeed. So that is something we need to remember when we think about an ordering. We need to think that the first variable is only affected by its levels, not by and the second variable is affected by the levels and lags of the previous levels of the previous variable and levels and lags of the current variable. So it's kind of like move forward. So R2, where when you're talking about R2, taking beta 2 on the right hand side, we have minus beta 2 1 1 0. R3 is 3-month yield, so beta 3 0 1. Probably it doesn't have any effect. 1-month yield is not important for 3-month yield. So we have how many? 3 square 9 unknown parameters in beta 1. D is equal to the diagonal elements, obviously. The short run restriction shows that the only contemporaneous relationship are R12 to R22 and R12 to R3T. R12 to R22 and R12 to R1T, I'm sorry, to R2T, R1T to R3T. So there is no contemporaneous relationship between R2T and R3T. That's why this part is 0 here. The parameters to be estimated are beta 2, beta 3, D1, D2, D3, beta 1. It's very simple because we have 3 parameters, 3 squared 9. That's all you need to remember. Monthly data. So we use US 0 coupon yields, which is from December 1946 to February 1991. Estimation is in 2 stages. In the first stage, a VAR1 is estimated with results. In the first stage of R1 is estimated with results given by this. So we are estimating a VAR1 in the beginning for R1T, R2T and R3T. And that gives us what? As we have estimated the VAR1 in the very beginning, in the first stage. In the second stage, the estimates of the beta and the D's are computed by maximizing the log likelihood function. We in C with T calls with the total observation. So first we specify the VAR1 model in the first stage. Then we maximize the log likelihood function from the reduced form equation with given number of observation, and we get S and where S is established as this equation. We already are familiar with this. So S is equal to root over D. We had D element, root over D divided by beta naught, and V is equal to SS transpose. So with this specification, the log likelihood function estimates, optimizes and estimates these parameters S and V, and also a value for the full information maximum likelihood function. The parameter estimates with standard errors based on Hessian matrix. So we can also find, if we ask the system to return Hessian matrix, we can also find the standard error. That's what is meant here. And then with V and S, we can also easily find the system by default finds beta naught and D when this relationship has been specified before, and hence the estimates of the short run impact at h is equal to 0. So at h is equal to 0, we have s root over d by beta naught. So very simply, this is the short run estimate, s transpose, and so we needed beta naught and d, and with that we are telling what the short run estimation is. In terms of long run, so s is equal to phi 1 f. Consider SVAR in previous example, except interest rates are expressed in first difference, and identification is now based on imposing the long run restriction that only shows that only shocks in R1T have a long run effect on all three. So in the long run, we are assuming that the interest rate has a long run effect on all three. There is no other contemporaneous relationship. So the parameter matrix looks like this. Only the first one has an impact on all three. Others do not have any contemporaneous relationship, and hence this has the parameters to be estimated in long run. So again, we do two-stage estimation, but first stage is the same as first stage before, where we specify the equation R1, R2 and R3, and they basically beta naught, the beta elements are estimated in the first stage with VAR approach, right, with the VAR method. What we do here is that according to VAR, each equation is estimated with OLS separately, and we have beta naught and D elements. So we do that, and we have phi 1. Phi 1 is I3, it's identity matrix. Phi 1 is identity matrix minus so the first stage is the same as for second, and now we're talking about second stage here now. Okay, first stage is as before. In second stage, instead of finding s, we are we're explaining the relationship of phi 1. First, phi 1 is independent matrix I3 minus a matrix here, which is, I'm not sure what it is, independent matrix I3 minus some given estimation. What is the equation that specified the relationship of autoregressive parameter? So if we have phi 1, or how we can phi 1 is identity matrix minus some other matrix here. Let me just have a look into it and find it out. So here phi 1 had, we know from s is equal to phi 1 f, the equation we derive when we estimate phi 1, we need the autoregressive parameters. So estimating phi 1 requires identity matrix minus, in case of a var2 model, identity matrix minus phi 1 minus phi 2. That gives you, in a var2 model, that gives you estimation of an autoregressive parameter phi 1 that will go into that will be multiplied with f to find s. So I minus phi 1 minus phi 2. In case of moving over h parameter, it would have been I plus psi 1 plus psi 2. So here exactly it's a var1 system. Because of var1 system, you already have an autoregressive parameter for var1 estimation. So identity matrix I3 minus phi 1, because it's a three variable equation. So I say you have phi 1 hat that you will so we have phi 1 hat that will be multiplied with f in the second stage estimation to find s. So we find s, and here v is equal to s transpose log likelihood function, all are these estimated. So after s we can find omega and log likelihood function. The maximum likelihood estimation automatically generates the values of s, f. So the estimates of short run impact at h is equal to 0 of three structural shocks in the three interest rates are s is equal to root over d by beta naught in terms of short run restriction, or I minus phi 1 f. You can also represent the short run restriction with this type of equation. Instead of is equal to phi 1 f, it is identity matrix minus phi 1 f. An important special case of SVAR models occur when beta naught is recursive. Under these, all of the parameters of theta can be estimated without any need for an iterative algorithm. So if your beta naught is recursive, then an iterative algorithm is not at all required. In chapter 13 we have seen in VAR decomposition, different types of VAR decomposition, all are giving numerically same results because we had recursive structure in beta naught. So SVAR becomes VAR. There is no SVAR estimation required when you have a recursive algorithm. So here focus is on maximum likelihood estimation in SVAR because we don't have any recursive algorithm. We are trying to avoid a recursive algorithm in this chapter. For example, if you have a recursive VAR, estimate VAR by OLS as before in chapter 13 we discussed to obtain VAR residuals, and then we could do maximize. If it's a Varma model, we could do maximize log likelihood function with respect to all these element s and d, and where v is equal to s transpose, the value of the log likelihood function, we receive the value of the log likelihood function, the standard errors, beta parameters, and d everything, right? So if the lower triangular part of beta naught contains some 0, the model is partially recursive. So if there is any 0 here, it's partially recursive. OLS estimates of the equation are still consistent but not asymptotically efficient, yet maximum likelihood estimation is not required as I can recall, and OLS is sufficient enough if you have a recursive structure in the system. So here I'm suggesting that OLS is going to be consistent but not efficient if we have if there is some 0 in the lower part of the recursive algorithm or the lower triangular matrix. To achieve asymptotic efficiency in this case, it would be necessary to use maximum likelihood estimation methods. So in this case it would be necessary, if the SVAR is non-recursive, OLS will not hold because there will be simultaneity bias arising from the presence of endogenous variables in each equation. Indeed, in this system MLE methods are needed. Alternatively, instrumental variable methods can be used to obtain consistent estimates following approach of Pager 1989. So the next topic is identification. Everything we have discussed in estimation is based on assumption that unknown parameters in theta are identified, where identification is based on the imposition of either short run or long run or sign restrictions. The issue of identification is now formalized. In the second estimation stage, the maximum likelihood estimation is found as the solution for omega expression as V contains n variances and n multiplied n minus 1 by 2 covariances. The maximum number of parameters from this set of equation is n plus 1 by 2. This restriction on the number of identifiable parameters is called the order condition. What is the order condition here? If you have n variances, the covariances will be n into n minus 1 by 2, but a maximum number of estimatable parameter are n into n plus 1 by 2, and that is, or identifiable parameter, that is order condition. That is a necessary condition for identification. So if you have two parameters, beta naught and d, at the second stage there are three cases that we can consider. So if your dimension of the parameter equals n into n plus 1 divided by 2, dimension of all the parameters theta equals n into n plus 2, then we can say v, the value of whatever we find with omega, that should equal to SS transpose. If the dimension of parameter is less than n into n plus 1 by 2, our omega will not be equal to SS transpose. There will be some small difference. We can verify this restriction by testing though, but that's an over-identified case. If our dimension is greater than n into n plus 1 by 2, dimension of the parameters, this is an under-identified case. So it's interesting, you see, in case of over-identified case, your n into n plus 1 by 2 will be more than the dimension. In an under-identified case, n into n plus 1 by 2 will be less than the dimensions. So in a case of over-identified system, we can verify the restrictions and there will be very small difference, we can still use it. But in case of an under-identified case, we have inefficient information to identify all parameters. We'll require more restrictions. So for over-identified case, we might not need more restrictions. We can do testing to see if these restrictions will hold. On the other under-identified case affirms we need more restrictions. So for example, order conditions of empirical SVAR model with two parameters. You see, we have talked about different models: Sims, Kim and Rubini, Blankert and Kua, Rapash and Gali, and Sims model was just identified. Kim and Rubini had over-identified model because dimension was less than n into n plus 1 by 2. Blankert and Kua had just identified, Rapash has just identified, Gali was just identified. So you see, Kim and Rubini was over-identified, but that still passed to be an important model, and that will be acceptable. A necessary condition for identification is a rank condition, which requires Hessian of the log likelihood function, n by 2 log pi minus n by 2 log omega 1 by 2t minus p u v transpose u. So that is the regular equation we are familiar with, as v is equal to SS transpose is the first order condition satisfied by maximum likelihood estimation. The rank condition is based on this following matrix: d vec v d theta prime equals d vec beta naught d beta naught inverse prime divided by d theta. What is vec? It vectorizes a symmetric matrix by retaining only the lower triangular portion of the matrix. Vec is a system of vectorizing a symmetric matrix that retains only the lower triangular portion of the matrix. So it's kind of like a system of stacking columns of X on and below a diagonal. So the column d vec v omega d theta prime. So we are basically representing this equation with a lower triangular matrix, and this is also so much for this. We'll see use of vec soon. So which has n into n plus 1 by 2 rows and dimension theta columns, and vec v represents n into n plus 1 by 2 dimensional column vectors of the unique elements of omega square. The rank condition requires the matrix has full column rank, while the order condition requires that n into n plus 1 by 2 rows are at least as great as the number of columns. Also, the rank condition requires the matrix should be full column, and order condition requires the rows should be at least as big as the columns. Very interesting. You see, if you have number of rows and columns equal, that is squared. But if you have more columns than rows, then there is something wrong. The rank will not hold. In case of a full column rank, you have more rows than columns. That's the common sense. LR Wald and LM test. In the second stage of estimation, important is omega, SS transpose, covariance matrix. In the second stage, covariance matrix in the second stage of estimation of VAR disturbances from the first stage. So this is the covariance of VAR disturbances from the first stage. If over identified, then this equation AV will not be SS transpose, but if restrictions are valid, so if V minus SS transpose equals X will not be statistically significant. So the difference, if restrictions, you have valid restrictions, then the difference will not be statistically that significant. And so a test of over identifying restrictions is based on comparing each element of the variance covariance matrix with each element of SS transpose. The hypotheses are if vec V SS minus SS transpose, vec is again, as I said, the lower triangular representation of the matrix only, V minus SS transpose equals 0. Alternative is if that is not equals 0. Remember, if there is any 0 element in the lower triangular matrix, then it's partially identifiable. So we do perform an LR test, and here log likelihood is the value of log likelihood function subject to over identification restriction. So log likelihood theta naught is the value of the log likelihood function subject to over identifying restriction. Theta 1 is the value of log likelihood function corresponding to just identified restriction. So theta naught, theta 1, restricted and unrestricted. Restricted is over identifying restriction, unrestricted is under identifying restriction. Under the null hypothesis that the over identifying restrictions are valid, LR is asymptotically distributed as chi-square with degrees of freedom equal to number of over identifying restrictions. Good. Degrees of freedom equals to the number of over identifying restrictions, so the number of restrictions. So you just take the nn plus 1 by 2, which is, well, maximum number of parameters, n into n plus 1 by 2 minus the dimension of your parameters should give you degrees of freedom. So there's an example over identifying test of interest rate model. So we have n equals 3. Interest rate model is based on recursive structure corresponding to just identifying case, where unrestricted is theta 1 and restricted is theta naught, using the results of over identifying model based on short-run restrictions. Log likelihood ratio test, we found it, and the difference between maximum number of parameters minus the dimension of each parameter is 1. So that is the degrees of freedom. So chi-square with 1 degrees of freedom, present value is 0. Clear rejection of over identifying restrictions. Alternatively, omega is unrestricted, SS transpose is restricted, Both are covariance matrices. Log likelihood ratio test is simply the log of SS transpose minus log of omega. So there is an example using the parameters of example. Our unconstrained var residual covariance matrix is this. The residual covariance matrix of SVAR with over identifying restriction is SS transpose. We find the determinant of omega and the determinant of SS transpose, and we take a log likelihood ratio test with the log of SS transpose minus log of omega, and we see the difference. So these are the testing method, and here ends the discussion on SVAR. Next we'll move on to the application, but before that something we need to talk about. Very simple stuff, but that we will need in our calculations. So first is any function will be used. So b equals any a determines if any elements are non-zero, any array elements are non-zero. So if you have a is equal to 0, 0, 3, any a tells you gives a logical array that the both first two columns are 0, the third one is 1. So create a 3 by 7 by 5 array and test to see if any of its elements are greater than 3. So be any element is greater than 3 or any element is less than 0. So any is automatically finding if there is anything that is corresponding to some value in our MATLAB. This is a MATLAB command. So matrix rows any a2. So if there is anything that is 0, so it gives us a 3 by 1 logical array. It's saying we are suggesting if there is any thing 0 that in our A in the rows, this matrix rows in the rows, so we get 3 by 1 logical array. Yeah, there are zeros, right? And the purpose of VEC is vectorizing a symmetric matrix by retaining only the lower triangular portions of the matrix. So basically the lower triangular portions are presented in a vector 11, 21, 20, 11, 21, 31, 22, 32, 23, 11, 21, 31, 22, 32, 33. So vectorizes a lower triangular element. So that is done by stacking columns of x on and below the diagonal. Whatever the process is, that is what VEC does, vectorizes a lower triangular element. So that is VEC. Vector error correction model of impulse responses. VEC model shows impulse responses. VEC command generates VEC model from impulse responses. So we have a VEC3 model. Okay, so delta yt is equal to phi 1 yt minus 1, phi 2 yt minus 2, phi 3 yt minus 3, phi 4 yt minus 1, yt minus 2, yt minus 3, et. So yt minus 1, beta 1, b3 sigma. Compute the autoregressive coefficient matrix that compose the VAR that is equivalent to a VEC3 model. What does happen in a VEC3 model? Was the VAR that is equivalent to a VEC3 model. VEC if b equals beta 1, beta 2, beta 3 columns, we are taking it, and VEC A equals to VEC2 VAR is a 4 by 1 vector, contains 2 by 2 VAR 4 model. VEC2 VAR. Oh, we are actually the VEC model is converted to a VAR model. It's a conversion. vector var, compute the autoregressive coefficient that composes the var that is equivalent to vec3 model. This is a vec3 model, right? Delta yt model, impulse responses, vector error correction. So 1 yt minus 2 yt minus 3, then simple yt minus 1, change in yt minus 1 and yt minus 1. Delta yt is equal to yt minus yt minus 1, right? We want to convert this to var, so we do vector var is a 4x1 vector. Vec is a vector element, vector to var. B sequence of 4x1 vector contains 2x2 var 4. It's a 4x1 vector contains 2x2 var 4. So I'm converting a vector to var. Error coefficient, it is in yt rather than delta yt terms. Compute forecast error impulse response on var 4. So forecast error impulse response on var 4. This is another function. If you have 20 number of observation, your impulse response is located in 2 rows 1 column. Locate in 2 rows of the first column. First impulse response is autoregressive ARMA IRF will give you the first impulse response function. The first impulse response function will be ARMA IRF will automatically estimate the first impulse response function. Lag matrix, something we already know. Is there anything else? Find is none if there is any non value. Vector is simply vectorization, and vector to var is from vector to var. Very simple. Minimum, maximum we know. Index to sub column, indices of a corresponding small element. Index to subsize a1 I minus row 1. So int to subject extract row and column indices of a corresponding the smallest value. So if I'm a I row and I column, so number of rows and column equals size of a I, we have 1 row. This is the position where the minimum value is located. Into subject gives you the position of the where the minimum value is located. It is located in first row in the second column. First row, second column is where the index is located. That's all. And the minimum of a gives you the smallest element. So int to sub size of your matrix and 1. Size of your matrix and 1 gives you where the location of the smallest value is. So that's all we need to know. for now, and hence we bring a conclusion to our discussion on SVAR theories. Next we'll move on to the applications of SVAR.